So I just wanted to finish up the problem that we started in class today. Unfortunately, I did not write down the exact problem that we started. So if these numbers right here are a little different from what we started in class, I apologize. I know that we are dealing with this compound right here, which is acetic acid. It's also known as ethanoic acid. And it's called ethanoic acid in the data booklet, but most chemists would refer to this as acetic acid. All right, so if we did 1.2 grams of that dissolved in 350 milliliters of H2O, all right, and again, if these are different than what you use, just go ahead and use these values right here. All right, so how are we going to go about this? Well, first thing, as we said, is we have to recognize that this is a weak base. All right, sorry, this is a weak acid. All right, and the way that we know that it's a weak acid is that it's not one. Essentially, it's not one of the strong acids. All right, there's another way that we can determine that. And that is by recognizing that it's in the data booklet under carboxylic acids, and they give a pKa for it. So anything that has a pKa in the anywhere from I guess 0.66 and higher is going to be a weak acid. All right. Notice you don't have any strong acids in this list right here. So again, this one entry right here, this is the formula we're talking about. That's ethanoic acid, and this is its pKa. All right, so the first thing that we want to do is figure out what the molarity of this acid would be in the water. All right, and so the way we can go about doing that is, first of all, figuring out how many moles of that acid you would have. Do a little stoichiometry. We would get this many moles. All right, remember we should round it to two significant figures because the smallest number has two sig figs. And once we do that, we can take that and we can put, that many moles over top of 0.35 liters, which is 350 milliliters converted to liters. And that would give us this molarity right here. Okay, so when you're doing these pH problems with weak acids, again, you want to, first of all, you want to write down the acid base or the acid dissociation reaction. And for this would be this reaction right here. Again, this would be considered our HA. This would be our A minus. All right, and we want to set up this chart. All right, where what we do is we start with the starting molarity of our acid. All right, and pretend that like we add that weak acid to water, and at that very instant that it hits the water, all right, let's assume that there hasn't been enough time for this reaction to occur. All right, well, at that point, this would be the concentration of that weak acid in the water. All right, but as time does occur, go on, this reaction is going to occur, and we're going to end up with a certain amount of this and a certain amount of this. All right, so at the very beginning, this would be the concentration of acetic acid. This would be the concentration of your A minus, and this would be your H3O plus. And the reason that these are both zero is at the very beginning there hasn't been enough time for them to form. All right, but over time it's going to this reaction is going to occur. So this, every time this reacts with water, it's going to go down by a certain amount, and the amounts of these are going to go up by the exact same amount. And the reason that they're going to go up by the same amount that this goes down is that the ratios are 1 to 1 to 1 to 1. All right, so every time one of these reacts, one of these gets created and one of these gets created. All right, so we could express the final molarities in the following way. The end concentration of this would be the 0.57 minus however many react, and the concentrations of these would just be 0 plus how many of them get formed, so that would be X. All right, so just a little side note, we can express the Ka of this particular weak acid in the following format. All right, remember we take the stuff on the right, that goes up on top, the HA form goes on the bottom, and we know from that data booklet that the pKa of ethanoic acid is 4.76, and that allows us to figure out that the Ka would be 1.73 times 10 to the minus fifth. All right, again, all you have to do is do 10 raised to the negative 4.76, and that would tell you what this is right here. All right, so what we're going to do is, remember, like just taking this expression right here, all right, this Ka, well, we're just going to use this, all right, because we know that that number is the acid dissociation constant for that particular acid. So we're going to say that that equals, all right, whatever these concentrations you have in the solution are. So remember, these are the N concentrations of these guys, so we're going to represent those with X's. This would be your concentration of your HA form right here, so that's what we can plug in down here. And remember, this is a relatively, this is a weak acid, and whenever you have that a relatively weak acid, when this number here, notice that this is smaller than 10 to the minus fourth, all right? So remember, 10 to the minus fifth is a smaller number than 10 to the minus fourth, all right? We can use this little assumption, all right, that this is we can basically get rid of that minus x, because since this is so small, we know that there is very little of this. We know that there's very little of this dissociation, all right? So that means that this x right here would be very, very small compared to this number right here. And if that's true, then this whole expression right here would be approximately equal to the number by itself, all right? So we can set x squared over 0.057 equal to this value right here. And if we solve for x squared, so x squared is going to equal this, we take the square root of that, it should equal this number right here. And since x also happens to be what our final concentration of H3O plus is, we can use that, because H3O plus, the concentration of that, is what you use to calculate pH. All right, so we just plug this number in for the concentration of H3O plus, and we end up getting a pH of 3.